when we reduce, see if the 1 and 2, 1 and 2, they are connected in parallel.
Parallel.
What's the formula? So what will be C12 equal to?
C1 plus C2.
Is
C1 plus C2.
exactly, that is C plus C, which is 2.
2C.
So this is equal to 2C. Now I can write this circuit now as now I had it till here. Instead of putting these two, I can just put one simple capacitor like this with the value 2C. This is C, this is C, this is C, this is C, this is the point A, this is the point B, and they are connected by the battery. Now coming to this, let me just name it again. This is C12, this is 3, this is 4, this is 5, this is 6. Tell me, how are C12 and 3 connected?
Series.
In series. See, so this is how you go. Wherever you go from the whichever are reducible, you see. So see, here 1, 2 and C3, they are connected in series. So in series, we reciprocally add them, right?
Yeah.
Here also we are going
Yes.
to add it reciprocal. Reciprocal addition means 1 by C123. When I write C123, I hope you understand this, that this means the equivalent one. Yeah. So this is 1 by C plus 1 by 2C, which is equal to 3 by 2C. So C123 is equal to 2C by 3. Okay. Now I'll reduce the capacitor evenly. So I can write this as this is the point A. Here is one capacitor. Here is another capacitor, and we have one more capacitor present over here, which is the B point. Now, instead of all of it, now we just have a single capacitor. I can replace the bigger one capacitor with a capacitor who has a value 2C by 3. Now, again, rest of them still have the value C, C, C. And we can say that this is C123, this is 4, this is 5, this is 6. Reducing it even further. Yes, Basmi, tell me, how are these two connected?
Parallel.
They are connected in parallel, correct. So we can say C123 and C4, they are connected in parallel. Parallel additions are the best here. You can simply just add it. So C123 4 will be C plus 2C by 3.
2C3.
That becomes 5C by 3. Now see here, last one. This is the point A. This is the point. Here we have one capacitor instead of all, because we have reduced this also with the previous one. Now this is 5C by 3. This is 3, this is 3, and this is our B. So this is C1234. This is fifth one. This is sixth one. Now we can just conclude for all of it. Can you tell me how are all these connected?
Series.
All of these are connected in series. So C1234 and C5 and C6, they are connected in series. So we need to reciprocally add all of them. So this will be finally, this is 1 by C equivalent. Now I can finally write because we don't have to reduce it further. This is the equivalent capacitor. This will be equal to 1 by C plus 1 by C plus 3 by 5C. Right, we are writing it in the denominator. So this will be equal to 3 plus 13, right? 3 plus 10. 13 by 5C is given by C equivalent. So finally C equivalent will be 5C by 13. Did you get it? How to solve such big questions?
Yes, ma'am.
Keep on reducing the circuit and do one thing, always draw whatever you're getting roughly. Like I had to draw it properly here, but you can draw a little bit roughly, and that will give you an idea what all things are present. Otherwise you'll forget. Okay, please write this, we'll see some more things.
Ma'am. Ma'am, can you scroll down?
Repeated?
Ma'am, 1 second. Yes, ma'am, done.
Okay. Um, see, just a small concept about the short circuit and an open circuit. Short circuit basically means that, see, if I have a bulb, this is a symbol for a bulb. So let's say if I have a bulb. Now, when the current is coming, or you can say charge is coming here, if the charge goes through this and comes across this, means it is going through it like this. So what will happen? The bulb will glow. This is what happens. Yes or no?
Yes, ma'am.
But what if I connect one more wire like this? Now what will happen? All the charges that have to come, instead of going straight through the bulb, they will go across this wire like this. And from this path, if the current flows, then what will happen? The bulb will not glow. Bulb will not glow. So what we can do, we can replace this. It means there is no significance of having this bulb, right? There is no significance. It's simply acting as a plain wire like this, where the charges are flowing. So this is what is called as the short circuit. Means your device will not glow, and it will simply, you can replace whatever device is given. Capacitor is given, resistor is given, anything which is given. You can simply replace your capacitors like a straight wire, or your resistors through a straight wire like this. Just replace it with a straight wire. Then there is a second case which is known as short circuit, sorry, open circuit. Open circuit basically means your wire is present and there is a cut in the wire like this. So what will happen? Charge will flow till here, no charge will come till here. So what you can do, you can replace this without any wire. Like you can just simply remove the wire. So if there is a capacitor where you feel this has been short like this, you can simply
Mm.
remove this wire from your circuit. Like if I have a circuit like this and I see this, I can write this circuit as this. Let's say this was 1, this was 2, this was 3. I'll just put 1 and 3 in my circuit. No need of the second wire when it is not functioning properly. Got it?
Yes, ma'am.
Okay, just write down these two note points. Then one more method of current, this voltage I'll tell you, potential divided method.
And can you scroll down? I'm done.
Now see what's meant by exponential divider method. Let me give you an example of a circuit. So, 3 capacitors are there. Like this. Okay, this is the circuit. A point, B point, let's say this is C1, C2, C2. And we have to calculate.
Ma'am, I can't hear you.
No, Basmi, I wasn't speaking. Am I audible now?
Yes,
Okay.
yes, ma'am. I thought you were speaking. There was some
No, no, no.
background noise.
Okay, no, no, I was just drawing the circuit. I'll just discuss it.
Okay, ma'am.
Okay, see, we have a circuit like this. Now, potential divider method basically says wherever you see, we have already studied how the potential divides, right? So wherever you
Mm,
have the potential, which can be the same, you mark them first. Like, let's say this is A point. Here, let's say the potential is some VA. Okay. So because of this wire, there won't be any disruption in the potential. It will be the same. That's what we have studied. Potential still remains the same
yes,
across
ma'am.
wires. Even this same thing we have seen. Even with branching, it doesn't get affected. So here also it will be VA. Means at this point also this will be VA. So we can say, see, till here it is VA. On this side it's VA. On this side it's VA. Agree?
Mm, yes, ma'am.
Now let's see, this is B point. So here there is a potential VB. So see, here also the potential will be VB. Across this wire also here the potential will be VB. Means here the potential will be VB and here the potential will be VB, right?
Mm,
Now we have studied wherever we have the same potential difference, same potential difference, we can say the devices are connected in parallel. That's what we've studied. That for parallel, they have to be
yes, ma'am.
connected in the same. Exactly. Now see, I am just drawing 2 points A and B, and let's see. Let me draw the center one. This is C2. Here the potential is VA. Let's say this is point A, this is point B, right? Across this, here we have C1. What's the potential difference? It is, wait, let me rewrite this. If you notice here, the potential difference across C1, it's
Mm,
VA minus VB, right? Same.
yeah,
Across C2 also, it is same, VB and VA. Like, if you want, you can write this as VA
yes,
minus
ma'am.
VB. And here also A and B both are there. So when you write, this is VA minus VB. All of these are having the same potential. It means they are connected in parallel. So we can reduce and write this circuit as this. This is your C1, C2, C3. This is point A, this is point B. Each of it is having the potential difference VA minus. So now this is easy to solve. Suppose the capacitance C1 is equal to C2 is equal to C3, which is equal to C. So my C equivalent will be simply C by 3. No, it will be 3C. And parallel we'll add it. it will be 3C. This can be the answer. So this was so difficult to solve, but reducing this simplifies our calculation, right?
Yes, ma'am.
So this is what is known as potential divided method. Write it down. Let's see this question. Then I'll come to the capacitor plates individually.
Ma'am, I'm done.
See, when we have here, Basmi, see, this capacitance is there, this capacitance, like 5 capacitors are connected like this. Now, here, these 5 capacitors are connected. If you notice one thing, can you tell me what is this? Can you identify this?
It will become a straight wire.
Very good, very good. Exactly. This is basically a short circuit. Correct, very good. And this isn't a short circuit. This case is a short
Mm.
circuit, so you can replace short circuit means there's a simple wire connected. Just remove your device and put a straight wire to ease your calculations, right? But if you look at this here, this is not a short circuit because okay, if current will not flow through here, current will flow through here, right? Short circuit means this only. Now
Okay,
this we have
ma'am.
already studied, right? If we reduce the circuit, let's say these three are connected, the three capacitors are connected in parallel. And instead of this one, the fourth one, I will just put a wire, and the fifth one will be connected in series with the three. So the three parallel will give us the resultant 3C for the whole parallel. And for the series, I
Yes,
can
ma'am.
just put the C. Now, our C equivalent will be 3C into C by 3C plus C, which is 3C square by 4C, which is equal to 3C by 4. This much of farad. Clear?
Yes, ma'am.
Okay. Just write this one.
That's been done.
Okay.
Yes, ma'am.
You've understood everything till here, Basmi? All the circuits that we have discussed, all these?
Yes, ma'am.
Okay, I'll give you some questions also for practice. See, uh, Wheatstone bridge, see, it's more there. We'll discuss the whole derivation and everything in the resistors chapter. Okay, I'll not discuss it in detail here. I'll just discuss it in detail in the resistors. But since we are doing the circuits, and there are chances that the Wheatstone bridge formation can be there in the capacitance, we'll be discussing this. So see, basically what happens in Wheatstone bridge is that there are five capacitors or resistors or devices connected. And they are connected in a manner if the bridge is balanced, there is a balancing condition. If the bridge is balanced, we say C1 by C2. The potential, simply you can say the potential difference across this, the two ends, B and D, which you can see, which are not connected with the wire. These two ends, can you see which are not connected with the wire, B and D? These 2 points. The four corners are there
Yes,
of the
ma'am.
square or whatever shape this is, a quadrilateral. Two edges are connected to the battery, one to the negative terminal, one to the positive terminal. other two edges which are not connected, if the if the bridge is balanced, the potential difference across them becomes the same. Now, what is this
Mm.
balancing condition? Balancing condition basically means C1 by C2 is equal to C3 by C4. If you see this, they are equal, like you will check, you will take their ratio C1 by C2, C3 by C4, you will check. If they are balancing each other, if you see the ratio is equal, it means this is balanced. Now see, if potential difference is the same, there won't be any charge flowing through it, right?
Mm. Yes, ma'am.
You this will act as an open circuit, right? No need of the wire. So you can simply remove the wire from your circuit. And when you remove the wire from the circuit, how will it look like? It will look like this. These two are connected. So look,
Mm.
can't you solve like this? These two are connected in series, these two are connected in series, and their resultants are connected in parallel.
Yes, ma'am.
Right? Understood this?
Yes, ma'am.
I'm just doing it in brief. I know I'm not discussing this in detail because we'll have to discuss it in very much detail in the resistor part because it's actually a portion from there. But if it comes through capacitors, don't get confused. This is how you have to apply. Am I clear?
Okay, ma'am. Yes, ma'am.
Then you can just remove this wire because there is no current flowing through it. There is no charge
Mm.
flowing. But your first step will be to check this. Okay? Write it.
Okay, ma'am.
Write it in current electricity. I'll start with circuit component.
I'm done.
See, now there are capacitor plates that can be modified and they won't be given. So see how you have to solve them. I'll show you the question first, then I'll tell you what are all these. I give you a question like this. Look, like this, if I give you, these questions come. These are some standard questions come, which I am telling you. So if a question is like this, these are parallel plates, and this is the point. Now you have to find out what's the net capacitance. See, first of all, quickly connect A and B with the battery. Now you know this is acting as your circuit. This is the positive terminal. See, it will charge this whole plate as positive. If this is positive, this complete plate will be positive. Yes or no?
Yes, ma'am. Yes, ma'am.
So see what will happen. This plate throughout will be positive. Like this. Okay, this is completely positive. And since the other plate is negative, this will be completely negative, right?
Yes, ma'am.
Okay. Now see how do we have to solve this? What did I tell you, Basmi? Can you recall how is a capacitor created or how can you create a capacitor? What did we study?
For energy.
Energy? No. How can you create a capacitor?
When you store an energy, right?
For?
When you store energy, it becomes a capacitor.
No. That I understand. You know the definition. That is correct, Basmi. But see, when you have two conductors, you oppositely charge them. Remember?
Yes, ma'am.
Okay. So see, it means wherever I see two plates, which have opposite charges. Now see, these can act as individual plates. It means I can write this as, look, this is one plate, this is the second plate, right? This one, this side. Then the third one, then the fourth one. This is the fifth one, this is the sixth one, this is the seventh one, this is the eighth one. 8 sides have been charged. But are all 8 of them capacitors? Will they be acting? No. Why? See, when I see the first plate, does it have any other negative plate beside it?
No, ma'am.
No. So it means this isn't a capacitor. Come to second. Does second have a negative plate near it?
Yes.
Yes. So see, let's say this they are separated by d distance. So this becomes one single capacitor. Similarly, can I say between 4 and 5th, will there be any capacitor or not? Yes or no?
There is. There
Yes.
is.
Yes. And between 6th and 7th,
There is.
there will be a capacitor. And 8th one won't be having. This won't have and this won't have, right? So 3 capacitors are created. Now see, if you see opposite polarities are connected like this. The opposite polarities are connected. They are connected in the series combination like this. And your capacitors are made. Simply what you do, one capacitor will be what? Epsilon naught A by D, right? This is what it is.
Yes, ma'am.
So when all the 3 of them, problems involving plates basically means when the opposite polarities are there, they are connected in series. When the same polarities are there, they are connected in parallel. All of them are connected with the opposite polarities. And see, straight away, this is a connection of series. All the 3 are connected together. These 3 capacitors. So simply you can say each one of them is this, right? So for 3 of them, what will it be? You have to reciprocally add it and values are the same. You can say C equivalent will be epsilon naught A by 3D. Why I wrote it in one go? Then all the values of capacitance are same in parallel connection. Let's say this. Not in parallel, sorry, in series. If all of them have the same value in series like this. Let's say C. Then take the capacitance and divide it by the number C by 5. I had the capacitance, I divided it by 3. Okay?
Okay, ma'am.
Write down this one, then I'll discuss some more things. I'll then discuss this example. Okay?
Okay, ma'am.
First, you write down this.
Can you scroll down? Ma'am, I'm done.
Thank you. if I give you this question, no? Look, when this parallel plate will be charged positively, here if I charge this plate negatively, can you look at the plates now? See, these two are making one capacitor, and these two are making one capacitor, right? So only two
Yes,
capacitors
ma'am.
will be present in your system. You'll just have two capacitors there. Because these are of the same polarity, they won't form any capacitor. That's what the question is all about. Okay? Simply you will have two times the capacitance. Whatever is the capacitance divided by two. Just draw this quickly. I want to teach you the dielectric slab problem. Please write this quickly.
Ma'am. Done, done.
Now just the last part of this. Dielectric slabs are given to you. So see, dielectric slabs can be given within the capacitors also, right? So you
Yes.
will see if the area is getting divided, distance getting divided. Like here it was very easy. You don't need anything. You can just identify the number of capacitors and that will give you the answer. But here it won't give, right? So what you do, check
Yes.
whether area is dividing or distance is dividing. Like if I see here, I see area is getting divided. Okay, what is C1? C1 will be C. We have the formula epsilon naught A by K times epsilon naught A by D. The formula for the first one will be K1 epsilon naught A by 2 and then D, right? And tell me for C2, this one, this plate.
K
A2
not
epsilon
D2.
what?
A by D2.
Yes, A by D. Now, these are individual capacitance. How to solve them further? Check through this. Okay, area is getting divided, they are in parallel. And in parallel connection, C equivalent is given by simply C1 plus C2. It will be K1 epsilon naught A by 2D plus K2 epsilon naught A by 2D. So we take epsilon naught A by 2D and we are left with K1 plus K. Got it? Easy? This part is easy? Did you understand it?
Yes, ma'am.
Okay. If the distance is getting divided, like I'll show you. Look here. area of each and every plate is the same. But see, the plates have been divided by 2. Distance has been reduced. It's like this is a single capacitor. In between, 2
Mm.
slabs have been fit. This was also a single capacitor. See, connected to this end, connected to this end. This is a straight single capacitor. But because of insertion of 2 dielectric constant, it has been created like 2 capacitors. Similarly, this whole capacitor is also created. So see, when I write C1, it will be K1 epsilon naught A by D is D by 2. So D by 2 will go up. Can you tell me C2?
A2 epsilon naught A2 by D.
Yes, correct. Same thing. So see, the distance is getting divided means they are connected in series. And series means 1 by C equivalent is 1 by C1 plus 1 by C2. So this will be D by K1 epsilon naught 2 plus D by 2 K2 epsilon naught A. We can take D by 2 epsilon naught A common and we'll be left with 1 by K1 plus 1 by K2. This is 1 by C equivalent. So see, 1 by C equivalent will be D by 2 epsilon naught A. When I take the LCM K1 plus K2 divided by K1 into K2. So C equivalent will be 2 epsilon naught A K1 K2 divided by D into K1 plus K2. Is that clear?
Yes, ma'am.
All right, then, Basmi. This completes with the chapter. Please note it down. And if you have any doubts to ask, please ask me. On Friday, I'll start with your current electricity. Please write it.
Okay, ma'am. Ma'am, can you scroll down?